Okay, good morning, everyone. I apologize for being a little bit delayed because I don't know who did this, but they certainly changed the adapter, and luckily they changed the adapter to VGA adapter. I didn't know why they did this and who did this, why did this, and fortunately I have another adapter which can fit to this VGA, so that we can continue with the class. Okay, so today we're gonna continue with our discussion about support vector machines. So for a quick review, in the last lecture, we used the sample complexity bound, the generalization error bound derived from the agnostic learning setting and the VC dimension, right, to motivate our learning principle for support vector machines, right? So the key idea is as follows. So based on agnostic learning, so what is agnostic learning? What's the key feature of the agnostic learning? A key assumption. Yeah, yeah. To be more concise, basically you won't assume the ground truth function reside in your hypothesis space, right? So that basically means like no matter how hard you try search over the hypothesis space, there always some gap between your learned hypothesis and the ground truth. In other words, you won't have zero training error. You won't be able to guarantee for any training data set, you can find a perfect hypothesis which perfectly predicts every examples in the training data. Now, so the training error is no longer guaranteed to be zero. Under that setting, and also consider an alternative metric to quantify the complexity or expressivity of your hypothesis space, because many hypothesis spaces are infinite, right? Like even linear models, the infinite space can be infinite. So we need an alternative complexity metric. Right? So we can derive, but we can still derive that with high probability. How high is the probability? At least 1 minus delta. The generalization error or the true error is upper bounded by the training error plus a term determined by the VC dimension of the hypothesis space, the delta and the number of training examples. Right? So this bound gives us many information regarding how you're going to improve the generalization performance, right? So if you want to improve the generalization error, you can try to minimize this bound, right? To minimize this bound, you can try to increase the number of training examples, M, right? The larger the M you have, of course, this term, the second term on the right-hand side will be smaller, right? It make your whole bound tighter, right? Or you can decrease the VC dimension. So the smaller the VC dimension of the hypothesis you have, it will make this gap term to be smaller, right? So right now, let us assume, okay, you're gonna have the same training error, that is the first term of this bound, right? And you're gonna have the same number of training examples. You're gonna have the same probability level delta, right? Then the question is that how do we choose the H, right? The hypothesis space such that I can make my whole error bound to be as small as possible. Right? So that motivates the design of our learning algorithm, right? So we want to learn a linear classifier which can have a small generalization error bound as possible, right? So this is called structure risk minimization principle, right? But here, there's one obstacle. One obvious obstacle is that, okay, because we're trying to think about like linear classifiers. If we consider the entire family of linear classifiers, you will find that the VC dimension is fixed. The VC dimension is D plus 1. So here D refers to the dimension of the input instance space, right? So that means like if you choose to search over the entire range of linear classifiers, you actually cannot reduce the generalization error bound. Okay. So that's a key problem, right? So the side step is that, okay, the workaround is that, okay, now that searching over the entire family of the classifiers seems like inefficient, right, ineffective. Right now, we just pick up a subset of linear classifiers, right? We just find out a classifier in a subset family, subfamily, right? And to find out a hypothesis, right? The benefit is that if you pick up subset of linear classifiers out of the entire family, you still have the chance to reduce the VC dimension. Right? That's the key idea. Then the question is reduced to how do we pick up those subset of linear classifiers? And then we introduced this so-called data-dependent VC dimension. We we use margin to index a subset of linear classifier. Specifically, we define H to be a set of linear classifiers that can separate the training set by a margin at least gamma. So you can imagine for this subset family H, every classifier will have a margin at least gamma. Okay? And of course, it is going to exclude many other linear classifiers whose margins are smaller than gamma. So that's why we call it a small subset of gamma, right? And then from this Vapnik theorem, we can conclude that the VC dimension of H will be upper bounded by 1 plus this minimum D and R square or gamma square. So R and D are just the features of the training data. So you don't need to worry about that. It's constant. Right? D is the dimension of your instance space, and R is the longest input vector throughout the training set, right? So, so then we can see that the only factor that affect the VC dimension of H is actually the gamma. So the larger the gamma you have, the smaller the VC dimension of the corresponding set of classifiers H, right? So that makes our chain of reasoning, right? So we could see that, okay, the larger the margin you choose, the lower the VC dimension of the corresponding set of linear classifiers. And then you can try to search the linear classifier in that small subset of family who has large margin and to minimize the training error. And overall, you'll find the classifier or the hypothesis you find H here will give you a tighter generalization error bound. Okay. So that's the key idea. So now if we push this to the limit, then we can summarize our learning principle as finding linear classifier that maximize the margin. So when you maximize the margin, you're essentially searching a linear classifier in a subset of linear classifiers, in a subset of family, in a subfamily who has the largest margin as possible, right? In our case, like if you look at all possible subset of linear classifier indexed by different margins, right? And that subset who corresponds to maximum margin actually has the smallest VC dimension. So you can imagine searching over that small subset of linear classifiers will give the smallest gap term here. And meanwhile, if you can guarantee that in that small subset of family, you still have a small error, the overall your generalization error bound will be almost smallest. That gives you best generalization performance. So that's the whole idea of SVM learning strategy. Any questions so far? Okay, perfect. So, so now we try to use this principle to construct a concrete objective function for our learning, right? So we start with like the most straightforward formulation, right? So now that we're trying to maximize the margin, right? So we start with the definition of margin. So remember, margin is the distance of the closest point in the data set to the separating hyperplane, right? So if we want to compute any data point xi to let me use pen here to draw something, right? For any data points here, right, and given a hyperplane, right? If you want to calculate the distance between this point and hyperplane, you just use this formula. You just use this formula, right? And here, because margin means that if a hyperplane has a margin, means that this hyperplane can correctly classify every example in the data set, right? There won't be mistakes. So that means this yi times w transpose xi plus b will always be positive or negative, right? And then divided by the norm of w. And then you go over every training example, your training data, you find out the minimum value. That is your margin. That is the margin of your current classifier, right? And then we know that in the outer level, we want to adjust those classifiers such that its margin to be the maximum. So now we formulate a nested optimization problem, right? So in the outside, we want to maximize the margin with respect to W and B, right? W is a feature vector, B as bias parameter. W and B decides the position of your hyperplane, right? And in the inside, because we need to evaluate under current W and B, what is the margin? That means we have to doing a minimization over all the training data points, right? You want to look at among all those training data points, which one is closest to the current hyperplane. So this is the most straightforward formulation, right? And here we before we try to simplify this optimization problem, right? We first give a common notation, right? So first, first in the distance calculation, right? The numerator, some people call this as geometric margin, right? And the whole margin is called geometry margin, but the numerator sometimes people call this functional margin. As to why people call the numerator as functional margin, I will explain it shortly. It actually relates to how we're going to simplify this. So okay, so we find that if we do this straightforward formulation, meaning that you're going to doing minimization across the whole training set and do maximization with respect to W and B, it will make your whole optimization procedure very, very challenging, because this is a nested optimization problem, right? In the outer level, you're doing a continuous optimization because your parameters, model parameters W and B are both continuous. But in the inner level, to get this gamma as a continuous function of WB, you need to first do some discrete optimization. Why this discrete optimization? Because you need to go over every data point and look at compare their distance to the hyperplane, pick up the smallest one, right? This is discrete. So typically solving this is pretty hard, and people don't want to directly deal with that. Then the question is that how can we simplify? Can we make our life easier? And we still want to fulfill the strategy that is maximize the margin, but we don't want to deal with this headache, right? This max min makes the discrete and continuous optimization problem. So the key idea is as follows. So if we recall the geometry of linear classifiers, right? So we see that for any linear classifier, it corresponds to a separating hyperplane, right? Algebraically, this hyperplane can be described by this equality. Right? The bias parameter plus the weight vector dot product with the feature vector is 0. Right? This is actually classified boundary. All the examples on one side of the boundary will be classified as positive, and on the other side of the boundary classified as negative. Right? So the key observation here is that because the prediction only cares about the sign, it doesn't care about the skew. So basically, if you multiply the model parameters, including B and all the weights, by any positive constant, it doesn't change the position, the direction of the classification boundary of the hyperplane at all, right? So we can multiply B W1, W2 here by 0.1, by 0.01, or by 10,000, by 1 million, by 1 billion. It doesn't change the linear classifiers at all, right? For every example in this instance space, you're gonna have the same prediction. So that brings an important insight, right? So actually, our numerical representations of those model parameters are actually quite redundant, right? Redundant means that, okay, say I have a particular instance of WB represent a linear classifier, right? But if you multiply W and B by some arbitrary positive constant, it still corresponds to the same classifier. It doesn't change, right? So that means like for any classifier, you will have like infinitely many weight vector and bias parameters, right? And they're just for those different weight vector and bias parameters, there's only a fraction difference, right? Does it make sense? Then I'm saying that, okay, if I want to learn linear classifier, it's not necessary to go over all possible space about W and B, because many W and B pairs that correspond to the same classifiers, right? And you search over the entire range of WB seems kind of unnecessary, and and also make your optimization procedure, right? As we just mentioned here, is pretty painful. Does it make sense? Okay, so now why not we just restrict the range of WB such that we can make our max mean optimization as we just formulated a lot easier. How can we make restrictions, right? So the inventor of SVM, they are really smart, right? So they try to skew up or skew down W and B such that the numerator of the distance is always 1. In other words, let us intentionally set the minimum function margin, namely the minimum of the numerator across the entire data set to be just 1. I just put these constraints. And then we actually do not need to perform like inner minimization, right? Because I have already tell you, okay, the minimum of this numerator or function margin across the data set is 1, right? Then your margin is automatically reduced to 1 over the norm of W, right? And we only need to solve the maximization problem. Does it make sense? So why this is true, right? Why can we make such kind of restriction? The number one reason comes from the insight we just discussed, right? You can, for arbitrary W and B, right? You can skew it to arbitrary level. It doesn't change the classifier at all, right? So now that this holds, right? Why not just to restrict the range of W and B such that my minimum function margin just to be 1, right? I put my, if this is our whole space of WB, right? The whole space of W, a model parameter space, right? So I can pick up a much smaller subspace of WB. As long as for every WB outside the subspace, you multiply some factor, some constant factor, you can find out a parameter vector inside this space. Then the classifier for this guy is exactly the same as classifier for this guy, right? So you don't need to search over the entire WB space. You just need to search over this small subspace. Right? So now I define the subspace to be all WBs such that the minimum function margin to be 1. And that's it. Okay. So this must relate to set WB to some constants, to skew WB by some constant, right? And you can imagine any WB outside this subspace, right? You skew it by this constant, you can find out a corresponding parameter vector inside this subspace. This is equivalent. So in this way, we can simplify our optimization issue. Right? We restrict our WB to be a smaller space, but it's still rich enough to include all possible linear classifiers. And then I just search over the best WB in this subspace to maximize margin. Right? In this subspace, we know the margin is simply 1 over W, norm of W. And you don't need to go over every data point and calculate which distance is 1. It has already tell you that minimum function margin, the minimum demargin is 1. Okay? And then you just need to maximize margin. You only have 1 level optimization left. Any questions so far? Does it make sense? Right? So this is kind of like a trade-off, right? So if I do not put any restriction on WB, then I have to deal with this painful double optimization problem, right? Because in the inner optimization, well, you do need to literally go over every data point and look at which data point is closest to the hyperplane and calculate the margin. And then, in the outer level, you want to maximize margin, right? So I don't want to do that, right? And how can we do that? How can we simplify this? Right? I'm not gonna search the entire WB space. Instead, I'm gonna carefully pick up a subspace. Right? In this subspace, every W and B can make sure the minimum of this yi W transpose xi plus B is 1. Because doing this is very simple because you just need to divide the skew of W by something, right? And you will ensure that for every possible WB, you skew it to some extent. Your minimum of this function margin will be 1, right? And then you just only need to look into all those skewed W in this subspace such that the minimum function margin is always 1. Okay? And then you just search over this small subspace and to maximize margin. And in this small subspace, we know that the margin is always 1 over the norm of W. You don't need to compare every data point which one is closer to the hyperplane. Any questions so far? Okay, seems like everyone is happy. This is really important. I want to emphasize this again, so please bear with me. But if you still feel a little bit uncomfortable, just follow the general strategy as we discussed, right? And all possible numerical representations for the linear classifiers are actually redundant. Why? Because for every possible WB pair, you skew it by arbitrary positive number. They corresponds to exactly the same classifiers, right? Actually, you don't need to search over all possible numerical values for WB, right? You just need to search a subspace. And it is rich enough to cover all possible linear classifiers in your space. And the SVM takes exactly this strategy. I'm going to restrict it to a smartly designed subspace such that the minimum of this function margin, like the numerator here, is always 1. So you don't need to explicitly calculate the minimum because you know it is 1. And then the remaining thing left is that, okay, you need to maximize with respect to maximize the margin with respect to WB in offset. Right? It kind of greatly simplifies our life. Yeah. Okay. So now, based on this idea, let us try to let us formulate as a optimization problem. Right? So we know that the maximizing in our simplified formulation, the margin now becomes 1 over the norm of W, right? So maximizing 1 over norm of W is equivalent to minimizing the square of norm, right? And here we put half as a constant factor in front of it, just for nice looking, just for convenience. If you want to calculate the gradient, you must have a factor of R, a factor of 2 in front, right? You got 1/2, you can cancel it out. Nothing else, you can remove it if you want, right? And then because we're going to restrict, because this simplified objective function comes from our restriction about the range of WB, right? The restriction is that you must have the minimum functional margin to be 1. And we need to explicitly describe this restriction in our optimization problem, meaning that we need to put constraints. That is, for every I, every training example, we have this function margin to be at least 1. Does it make sense? Right? So this constraints actually specify the subspace of WB we're going to search over. And this subspace, this constraint specify this subspace WB that for every WB in the subspace, the minimum function margin is 1. Right? And under this subset, we know that the margin is 1 over the norm of W. So maximizing this margin is equivalent to minimizing half of the norm of W. Okay. That's the key idea. Okay. So to repeat, right? The objective function here becomes a simple quadratic objective, right? Half W transpose W. This is essentially to minimize, it is essentially to maximize 1 over norm of W corresponds to the margin, right? And those conditions, those constraints is just to specify our restriction on the range of WB space, right? To make sure that the minimum function margin is always 1 thing. Okay, so this is called hard SVM or hard support vector machines. And we'll look at how to solve this optimization problem later, right? But there's some problem with this hard SVM. So what's the problem? Any thought? Tuning error to be 0. Yeah, we need to tune near 0. Yeah, exactly. So how can you say this from the formulation itself? Can anybody say is the issue, right? The issue he proposed is perfect, right? So this hard SVM kind of requires you have a 0 tuning error. But how do you see this? Just from out of this formulation, how do you see this requirement? Any thought? Okay, let us just try to recall, right? When we say when we have a linear classifier WB, right? And we want to use that to make a prediction on an instance X, right? And suppose the ground truth label is Y, right? How do we check if my prediction is correct or not? Yeah, of course, this is the most straightforward, right? We just look at the sign of our, classification score and compare it with the ground truth label, right? But we talk about another way of doing this, right? We do not need to explicitly take the sign of the score. We talk about that. Okay, we can multiply the ground truth label with the prediction score, right? Right. Yeah, this is just a quick refreshment of our previous discussion, right? So if this guy is non-negative, it means you make a correct prediction, right? So now, if we look at the constraints in our hard SVM formulation, you see that we not only require the product between the ground truth label and the prediction by WB to be non-negative. We're doing this even more strongly, right? We require for every example, this product to be at least 1. This is a very strong requirement, right? So it basically means that at least it means that, okay, you have to correctly classify every example in your training set. Your training error must be 0. This is actually not realistic in many settings. As we mentioned before, in practice, it's unlikely that you're assuming your data set is so simple. You can find a separating hyperplane, you can find a line to well separate them out, right? Probably the data set is mostly linear separable, meaning that if you can smartly exclude some outliers, you can still find a separating line or hyperplane, right? But it's unlikely that data set is so well so that and it's separated so well you can find a line. So if the data is not separable, that means no matter how you choose WB, there will always be some incorrect prediction, right? By incorrect prediction, it means that this product will be a negative, right? For some example, at least. And that means like those constraints cannot be fully satisfied. Then the optimization will give you empty results, right? Because you cannot find any WB which satisfy all the constraints required, right? And it will tell you, okay, your optimization problem is infeasible. Your feasible region is empty. Any questions so far? Okay, so then there comes a problem, right? Okay. How to address this problem? The original hard SVM formulation is a constraint optimization problem. If the data is not separable, there is no W and B that will classify the data correctly, right? And then your constraints cannot be fully satisfied. It means the optimization problem is totally infeasible, no solution, right? And how can we adjust our hard SVM to be more robust and to be more realistic to account for non-separable data? So here we give the example, right? So suppose this is my data set, and you see a large portion of positive examples and the vast majority portion of the positive examples, the negative examples are linear separable, except a few outliers, right? Right. Suppose you get rid of these 2 annoying outliers, you certainly can find a hyperplane to separate positive and negative examples, right? So now we want to allow our SVM model to gain some kind of flexibility and to automatically pick up those outliers, to kick them out, and then finding the separating hyperplane for the remaining. Okay? So how can we do this, right? The idea is that, okay, we're going to allow some examples to break into the margin. In other words, we're going to find out a separating hyperplane for most of the examples. And for the remaining outliers, we can allow them to break into the margin or even misclassified by the hyperplane. Okay? And then the margin is only computed for the remaining data set, because for the remaining data points, they can all be correctly classified, and we can only have a margin for that data set, right? And we only leave the outliers to be excluded. Okay? So although this could like introduce errors, right? Because you're gonna sacrifice you're gonna ignore your performance on several outliers. In predicting these outliers, you probably can increase your training error a little bit, right? But because you can still, but for the remaining, say, a majority of data points, you can find a large margin classifier. This term, right? The second term can be small, right? And overall, the training error plus this gap term can give you a tighter generalization error bar. So that's the idea. So let's see, how do we formulate this, right? Okay. So the hard SVM requires that for every example, your WB will has this function margin at least one, right? So now because we could allow some examples to break into the margin, but we do not know which examples can break into the margin beforehand, right? We should allow our learning algorithm or optimization algorithm to automatically identify those outliers to let them break into the margin. Right? To enable this, right, we're gonna, for every example, introduce one slack variable, KCI here. Right? So KCI is non-negative, right? But then with KCI, we can relax our constraint to be the function margin to be just no less than 1 minus KCI, not 1. So what does it mean? It means that if KCI happens to be 0, then this constraint will return to the hard SVM case, right? So this constraint becomes the function margin is no less than 1. Meaning xi, yi will stay on the function margin, outside margin, right? But if KCI after our learning procedure turns out to be a non-zero, right? To be positive, absolutely positive, right? See 0.5. That means your xi, yi could break into the margin, right? Could intrude the margin. And as to which particular examples should be excluded outside margin or break into the margin, will allow the automatic optimization over those slack variables, KCIs. Does it make sense? That's the meaning we introduce this slack variable KCI for every training example. Okay, and then we come to our new formulation, SVM, which we call soft SVM. Why it is called soft SVM? Because it can deal with non-linearly separable data set, right? And it allow flexibility to exclude some outliers of the data to be account for the margin and allow them to break into margin or even to be misclassified by our linear classifier, right? So first we can see that the constraint is now changed for every training example. We have a corresponding slack variable Ci, which is non-negative, and your function margin, yi w transpose xi plus b, is no less than 1 minus Ci. And then in the objective function, right, it becomes half square norm of w plus the summation of all the slack variables. And here, C is the hyperparameter, indicates the trade-off. Right? So now I want to ask, why do we change the objective function as well? So in the hard SVM, we know that the objective function is just half square norm of w, right? But now in the soft SVM, in addition to that term, which corresponds to a margin, right? We also add a summation of the slack variables, right? What's the meaning of doing this? Why not we just erase this term, right? Just keep the same objective as in hard SVM. Any thought? Can we be a little bit more specific? I think, I think what you said is right? I just want you to be more detailed, yeah. Yeah, what kind of flexibility you don't, what kind of freedom you don't want them to have? Very large, very large. Okay. Yeah, okay, that's totally fine. Okay. So first, to see this problem, right? We know that, okay, the reason we introduced the slack variables to Ci is to allow some examples to be treated as outliers so that they can break into the margin, right? Break into the margin of linear classifiers, it can be misclassified and so on, right? So Ci, when it's non-zero, or in other words, to be bigger than zero, means that the corresponding example I can break into the margin, right? And Ci represents in how much degree, how much extent your example can intrude margin, right? So if in our objective function we exclude this term, right? Imagine what will happen. If we exclude this term, that means, okay, our objective is just to maximize margin, right? You have the flexibility to exclude whatever data points you want, as long as for the remaining data points, you can find classifiers who has as large margin as possible, right? Then you probably will have some extreme case, right? If you take a look at this guy, right? What extreme case like? I'm gonna try to exclude all the data points except two farthest pair of positive and negative examples, right? Because for this remaining two examples, they are farthest to each other. Then I find the linear classifier, of course, my margin will be the largest, right? But the cost is that I'm going to throw out all the other data points and allow all of the remaining points to break into a margin, and I can misclassify them. Will that lead to a good linear classifier? Why? Yeah, but why misclassify everything will lead bad classifier? Yeah, that's the intuitive answer, right? If we associate with the generalization error bound we have here, right? We'll see the reason, right? So you see the generalization error bound actually consists of two terms, right? One term is the training error. The other term is a gapping term, which is, determined by the visit dimension, right? So if you allow the maximum flexibility to kick out a bunch of data points and maximize margin, of course, your visit dimension could be the very, very minimum, right? So you can make this gapping term to be as small as possible, but you largely increase the training error. Why? Because they exclude them. You allow them to break into a margin, you're going to misclassify a lot of them, right? So that means, okay, although you can kind of to the maximum extent to reduce the second term, but you largely increase the first term, the training error, right? Your overall generalization error bound won't be the optimum, right? Won't be the smallest. It could be overall still large, right? Does it make sense? That's why we need to find some trade-off, right? We don't want to exclude so many data points as outliers and just optimize margin for the remaining data points, because that will increase the training error. Instead, we want to minimize this summation, right? So we know the summation of PCIs actually indicate how many data points can we allow to break into the margin to be misclassified, right? We want the number of data points which can be excluded and break into the margin to be as small as possible, so that we can reduce the training error. Right? And meanwhile, of course, for the remaining data points, we still want to maximize the margin. Right? So by adding these two terms together and add a trade-off hyperparameter C, we can allow this trade-off, right? We can seek the trade-off, okay, between how many data points can be excluded for the margin maximization to increase the training error, right? And also the margin maximization. So this leads to our final formulation of SVM, right? So the first term represents our goal to maximize margin. The second term, which minimizes total slack variables, is trying to allow as few examples as possible to violate margin, to intrude margin. And this hyperparameter C indicates the trade-off between them. You can basically view it roughly as the trade-off between the first term in the generalization error bound, the second term in the generalization error bound, right? But because the generalization error bound, see here, the generalization error bound, the first term is the training error, right? So the smaller training error you have, the fewer examples you would like to allow them to violate margin, right? And the second term is determined by the margin, right? And of course, the more examples you allow them to violate margin or exclude them, the more likely you're going to have a larger margin, right? So you have to set some trade-off. Okay, any questions so far? Is everyone happy? Are we happy? Yeah, feel free to interrupt with me or ask me to clarify anything. Otherwise, we're going to assume we're on the same page, everyone is happy, right? But again, the design, as we'll discuss later, the motivation of SVM, the design of the SVM formulation, and also the whole algorithm framework is a masterpiece of art, right? It's very, very smart. We'll see that later, right? Okay, so let us consider how do we optimize this problem, because now we have a formula training, the training procedure, which essentially is to solve this constraint minimization problem, right? So the first strategy to optimize this soft SVM problem is to eliminate the slack variables, because you kind of introduce these additional slack variables to allow extra flexibility, right? So during the optimization, I don't want to optimize so many variables, right? So I want to look at if there's any ways such that I can get rid of this CIs. To do that, right? If we just arrange the first constraint, right? We can write it as CI equivalently is no less than 1 minus function margin. And the second constraint obviously is CI is no less than 0, right? So now I want to ask, under these two constraints about CI, what's the minimum value of CI? Yeah, let me repeat this question, right? So by this simple rearrangement of the constraint, right, we can view that, okay, this is our objective function. And then for every training example, I have two constraints for the slack variable CI. Right? First, CI must be no less than this guy, right? Second, CI must be no less than 0. So now remember, because we're doing minimization of this half W transpose W plus C plus sum over every CIs, right? So can we, from the constraints, directly derive the minimum value of each CI? Y is 0. Yeah, you're thinking in the right direction, but the answer is a little bit wrong. So remember, this is a constraint optimization problem, right? So that basically means like if you want to make your problem, if you want to make your learned model parameters to be valid, right? It must satisfy all the constraints. So it means whatever CI values you choose, right? The optimal value of CI must satisfy both inequalities. Right? And then the minimum CI would be the maximum between the two, right? Because only when CI to be maximum between the 0 to it will satisfy both constraints, right? Right. And the minimum value will be exactly the maximum of two lower bounds, right? 0 or 1 minus yi w transpose xi plus b, right? And of course, CI can be even larger, but that won't be the minimum one. Right? The minimum of CI will be the biggest value between 0 and 1 minus the function margin, right? And that will guarantee CI not only be minimum, but also satisfy both constraints. Does it make sense? So in this way, actually, we have solved the CI in terms of any W and B, right? Because for any fixed in W and B, we know the minimum CI will be the minimum between, or the maximum between 0 and 1 minus function margin, right? So the remaining problem is to optimize W and B. And because we do not put any constraints on WB, so we kind of like reduce this problem to be an unconstrained minimization problem. The objective will be half W transpose W plus C sum over every minimum value of CI. Okay. Any questions so far? Okay, so before we talk about how to optimize this problem, right? Because this problem now is further simplified to be just an unconstrained optimization problem for only W and B, right? Let us look at what does this simplified objective function tell us. So in this objective function, right, we have two terms. The first term, half W transpose W, we know is it has meaning to maximize margin, right? Because the margin is 1 over the norm of W, right? You maximize margin is equivalent to minimizing the norm, square norm of W, right? But what does the second term mean, right? the second term is derived directly from the minimum value of each KCA we can get, right? But if we look at this minimum value, what does it reflect? Yeah. Yeah, exactly, right? Remember this guy, this yi times W transpose xi plus b, as we mentioned before, right? Like ground truth label multiplied with the classification score indicates whether you're doing correct or doing wrong, right? So we inject this product into this maximum value. Actually, it reflects some kind of penalty for the prediction, especially when you make wrong prediction, right? And let's do a little bit of analysis, right? We can consider three cases, right? So first, this example XIYI is not only correctly classified, that means the product is not only not negative, but also the example is outside the margin. So outside the margin means that this function margin, this product could be no less than 1, right? From our formulation, right? Remember, we cannot restrict our W&B space such that the minimum function margin mean here is the product between yi and the classification score is at least 1, right? So if the point stay outside margin, it just means this product must be no less than 1, right? So if in this case, the example not only is correctly classified, but also stay outside the margin, then 1 minus this function margin will be negative, right? Because yi W transpose xi plus b is no less than 1, right? And you subtract 1 by this guy, it will be negative, right? And the maximum y will be 0. Right? Right? So that means the whole maximum value is 0, and it reflects that for this case, you won't have any penalty. You won't receive any penalty. The penalty is 0. So the second case, right? The second case that your classification is wrong, right? And your classification is wrong, it means that this guy, this product is negative, right? Of course, you subtract 1 by a negative number, you're gonna be bigger than 1, right? And then the max between 0 and 1 plus something, right? Will of course be bigger than 1, and you receive a penalty as 1 minus yi W transpose xi plus b, right? So you see that you receive some quite big penalty if you make a wrong prediction. Mm-hmm. Yeah, this is derived from optimization, right? But why one stays here? Yeah, exactly, as you said, right? Because at the beginning of our problem formation, we use some trick, right? We kind of restrict our space on WB to be inside a small range whose minimum function margin is 1. That's why 1 stands here. Okay, so the third case, this example XIYI can correctly be classified, but the margin, this example is too close to the margin. Right? That basically means this guy is non-negative, but less than 1. In this case, it means that, okay, although you can correctly classify this example, but this example is too close to the hyperplane, right? And then you see that 1 minus some value smaller than 1 still be positive. So that means your maximum between 0 and this guy will be still 1 minus yi w transpose xi plus b, right? So it implies that even in this case, you still receive a penalty, and the penalty is 1 minus yi w transpose xi plus b. Okay. So we see the interesting point here, right? So if we make a wrong prediction, you're going to receive a big penalty. If you make correct prediction, you still has possibility to receive a non-zero penalty. Okay? Only when your example is enough far away from the separating hyperplane, you're going to receive zero penalty. So this penalty is called a hinge loss, right? Hinge loss function. Right? This is directly derived from the SVM classifier. Right? So remember, in our linear regression case, we have a square loss function, right? We just calculate yi subtracted by your prediction, which is w transpose xi plus b, you take square, right? This square loss, right? But for the SVM formulation, right? Through a series of optimization problem formulation and also simplification, you end up with this a little strange loss function is called hinge loss. Okay, so let's place hinge loss in a figure, right? Let's see what happened, right? So the y-axis is this figure indicates the loss value, the loss function value. The y-axis represents the yi times w transpose xi plus b, the function margin, right? So this black curve indicates the hinge loss. So you can see that only when your function margin to be at least 1, you have zero loss, meaning that you don't receive any penalty, right? And of course, when your function margin to be negative, meaning at this region, right, you're going to receive a relatively large penalty because you make a wrong prediction. But in the middle, right, in this region, your function margin is positive, meaning that you are able to correctly classify this example. But your example is too close to the hyperplane. Then you still receive some penalty. So this is the property of the hinge loss. As a comparison, we can take a look at the ideal so-called 0-1 loss. Right? 0-1 loss, which is the red curve here, right? Is red lines here. Right? 0-1 loss just saying that, okay, if you make correct prediction, I have a no penalty, which is 0. And if you make a wrong prediction, then my loss is 1. And hinge loss is an upper bound of the 0-1 loss. Right? Any questions so far? Okay. Right. So to emphasize again, right, the hinge loss, in the hinge loss, this black line above the red curves, which is the 0-1 loss, right? The hinge loss will make the incorrect prediction to get a linearly increasing penalty with the value, absolute value of your score. Right? It's a line, right? Meaning that the more your function margin toward to the left, right, meaning that the more extent you make a wrong prediction, you're going to receive a larger penalty, right? And if your classification score is far away from 1, meaning that if your function margin is larger than 1, right, is far away from 1, then you don't receive any penalty. But in the middle, even your prediction is correct, but you're still within the margin of your classifier, you can still receive some penalty. So you can imagine hinge laws trying to find a separating hyperplane to be as far away from all the data points as possible. Okay. Okay. So now we can talk about the general learning principles. Right? If we define our training loss, right, over every training example, right, which measures how much penalty you're going to receive using your current model to predict the example, right? And the learning is to find the hypothesis that has the lowest loss on the training data. So adopting such kind of strategy is called risk minimization, right? So the least mean square regression and also the perception learning algorithms all adopt this kind of risk minimization principle because they don't have like a constraint about where and how should we place those weight vectors, right? I can just optimize my W and B such that my training loss to be as small as possible. So this is called risk minimization. But in the SVM formulation, our learning is not just to minimize the training loss, but also we want to regularize the learning such that the hypothesis, the linear classifiers, to have a large as much as possible, right? So if you could remember, like, yeah, our learning objective, right? In SVM, we have two terms. The first term, half W transpose W, corresponds to minimizing or maximizing the margin of linear classifiers, right? And the second term is how well you fit to the training data, which we had just explained. It is called hinge loss. And the training actually is the trade-off between the two. Is the trade-off between some kind of regularization and how well you fit to the training data. And this kind of like learning principle is called regularized risk minimization. In this regularization term, right, we in general define a term to penalize over complex hypotheses. Okay, so if we go back to look at the SVM objective function, right? And clearly it is a regularized risk minimization principle. You have a explicit regularization term, and in SVM context, it corresponds to a maximized margin. And you have a hinge loss term, which measures how well you fit to the training data. And your learning amounts to finding the best trade-off of these two terms, right? So, but in a more general strategy, we do not necessarily to restrict our regularization to maximize the margin, right? You can come out whatever reasonable regularization principle you want to inject. It depends on you, right? And also, we do not need to restrict ourselves to use the using the hinge loss, right? You can come out a variety of other loss functions which imposes other preferences or your domain knowledge. So actually, we can generalize the structure of SVM objective function to include a larger family of classifiers, right? And we allow the flexibility to design new regularization terms and flexibility to design new training loss terms. And eventually, we usually need to introduce a hyperparameter that controls the trade-off between the regularization and the training loss. So that's the general framework for regularized risk minimization principle. So any questions so far? Okay, great. Again, we want to encourage everyone to follow through the slides and trying to understand how the SVM formulation is motivated by the generalization error bound, and then reason under a series of logics and give us the principle to maximize margin, and then through this simple, straightforward, naive formulation by introducing the idea to restricting the WB space, right? And introducing additional constraints and simplify the constraints to get the regularized risk minimization form, right? Okay, so in the next lecture, we'll talk about how do we efficiently optimize this objective function. Okay, see you on next Tuesday.